Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Hi everyone, welcome back to SIC1004 Thermodynamics. So this is lecture 4. I hope everyone is staying positive wherever you are. All right, let's move on to our attendance. So this is for the March 16th attendance. Again, please scan this, fill in using your new matrix number code without the slash number. Right, let's recap what we have done previously. We talked about spontaneous and non-spontaneous processes. Also the PV plots for isothermal processes and also adiabatic processes. The isothermal and adiabatic processes. And we talk about the partition function that leads to this equation delta U is equivalent to equals to 3/2 nR delta T. We define what specific heat capacity is, and also the relationship between Cp and Cv, in which Cp is the heat capacity at constant pressure and Cv is the heat capacity at constant volume. Right, today we're going to talk about the other physical entity, thermodynamics entity, which is enthalpy, and that enthalpy is symbolized by the letter H. Now, enthalpy is given by the internal energy plus PV, and because at most of the time, the chemical reactions that we perform is always conducted under constant pressure and with reversible work. So enthalpy seems to be a useful function, state function in these conditions. Right. So usually we don't measure enthalpy directly. We're concerned with the change in enthalpy delta H, and delta H is equivalent to HF minus HI. So for endothermic reaction, right, the delta H will be positive. And for exothermic reaction, where heat is being released, the delta H will be negative. And I'm sure this is not the first time in which you have seen or heard the term endothermic and exothermic reactions. Now, we have, as we go along, I hope you tie back with the previous equations that we have already covered. And we have covered from the first law of thermodynamics what delta U is. And and also what work is, as well as also the relationship between delta U and W. Now we want to incorporate delta H into the equation. Now we know that H is equals to U plus PV, and when you actually express that in delta H, okay, so what you have is delta U plus delta PV, and this will be expanded to P delta V plus V delta P. Now, because delta U is equivalent to Q minus P delta V, so you can plug that into this equation, and so you finally get delta H is equals to Q plus V delta P. Now, because most of the chemical reactions and biological processes occur at normal atmospheric pressure, which is a constant, so this expression becomes 0. That leaves delta H to equals to Q. And so really delta H really defines the heat added or lost in the system when you have a process going on under constant pressure. So you have a subscript P here to signify that it is a constant pressure. Right. So sometimes the delta H is represented via an energy diagram. So this is an example of an energy diagram to quantify the heat flow in and out of a system in a process at constant pressure. All right, so here's an example of an exothermic process where heat is given off, right? And here's a process, the formation of mercury oxide, from mercury oxide, and you break it up to mercury and oxygen is an endothermic process, right? Now, I have to say that enthalpy is one of the easiest concepts to actually understand, even the problems, the mathematical problems. Right, so the enthalpy change for reaction is described by the H final minus H initial. All right, and in some cases, if you're talking about reaction, you also can do that via taking the H products minus that of the H reactions. Hence, you have the enthalpy of reaction. So hence, thermochemistry is the study of heat change in chemical reactions. So for example, when you have hydrogen plus oxygen and you have this H2O, it gives you delta H is equivalent to minus 483, which indicates that this is an exothermic process. And when you want to represent that in terms of an energy diagram, so this is how you're going to sketch this, right? So enthalpy is an extensive property, so it depends on the amount of the reactants. Doubling the reactants double the amount of enthalpy, and it also depends on the state of the reactants and products, whether it's a gas, liquid, solid, or aqueous. That has to be specified. So when you have this methane plus oxygen gives you carbon dioxide and water as a gas. The delta H is minus 802, but if the product gives you water as a liquid, that gives you delta H equivalent to minus 846 kilojoule. And if you actually have, and so on for in this case, right? Okay, so it depends on the state of the reactants and the products. So yeah, this is just an example of another energy diagram. All right, so you can read this for yourself. All right, the magnitude of delta H is directly proportional to the amount of reactant or product. So the first thing that, first of all, when you have a question on this, you want to make sure that, first of all, your reaction is balanced, all right? And the delta H for reaction is equal in magnitude, but opposite in sign to delta H for the reverse reaction. So what do I mean? It means that if I have hydrogen plus oxygen gives you H2O here, it gives you delta H equals to minus 483. If I were to reverse this reaction, that means the signage for delta H is also reversed. So now that this is reversed, so the signage becomes positive. It's negative here and it's positive here. Hope that's clear. All right. Now, let's look at an example. Given the following thermochemical equation for the combustion of methane, how much heat energy is released when 2 grams of methane is burned? Now, don't be in a hurry to quickly answer this. You have to make sure that this equation is first balanced. So 2C there, H, this 4, and there are 4 oxygen there. So it's balanced, give you delta H equals to minus 802. All right, how much heat energy is released when you have 2 grams of methane burn? So 1 mole of methane produces 802 kilojoules of heat. So if you have 2 grams of methane, that gives you 1/8 per mole. And so 1/8 per mole will actually produce 100.25 kilojoules of heat. All right. Second example, given the following thermochemical equation for the decomposition of mercury oxide, write the thermochemical equation for the reverse reaction. That's very easy. If this is first, this is balanced, then if this is positive, the reverse will surely be negative, as you can see here. Now, the stoichiometric coefficients always refer to the number of moles, all right? So here again, if you reverse the sign, that means that if you multiply both sides by a factor of n, so you must also multiply the delta H. So if you multiply 2 here, all right? So you have to multiply the delta H as well. So now it becomes 12.02. Now, for any reactions, chemical reactions, there will be that the corresponding enthalpy. So you can have heat of neutralization, heat of ionization, heat of polymerization, heat of fusion, heat of vaporization, heat of reaction. All right, so you have various examples of delta H. So the standard enthalpy of formation, there's no way to measure the absolute value of enthalpy of a substance. So there is a standard arbitrary scale as a reference point, which is called the standard enthalpy of formation. All right, and it's the heat change that results when 1 mole of compound is formed from its element at a pressure of 1 atm. Now, the standard enthalpy of formation for any element in its most stable form is 0. So for delta H formation for oxygen, for example, is 0. For graphite, it's equals to 0. All right, and usually a table is given to you in this as such. All right, so any general chemistry textbook will have this. All right. Now, the standard enthalpy of formation of HCl can be measured from the heat of reaction. And so hydrogen plus chlorine becomes HCl. So the enthalpy of formation for 1 mole, right? You need it in 1 mole will be given. So you need to divide that by 2. That gives you just 1 mole of HCl. So the standard enthalpy of formation for HCl is minus 92 kilojoules per mole. Now calculate the enthalpy of formation of aluminum oxide from the following combustion. Now this gives you 2 mole, so you only need 1 mole of that. So divide by 2, divide by 2, divide by 2, meaning that this has to be divided by 2. So you get that delta H to be minus 1669 kilojoules per mole. So there are 2 ways actually to calculate the standard enthalpy of reaction. So I'd like to apologize if you hear any noise pollution. All right. So this the standard enthalpy of reaction, as I said, is related to the formation of the products minus that of the reactants. It's just like the Hess's law. When the reactants are converted to products, okay, the change in enthalpy is the same whether the reaction takes place in one single step or a series of steps. So it's a state function. It does not matter how you get there. What you need to know is only what's the initial and the final state. All right. And so you have something that looks like a simultaneous equation. So you have two reactions here, all right? And so you want to find what is the enthalpy change for NO2. So looking at this, so you have two equations that gives you different delta H. Now find the enthalpy change for the formation of NO2. So here you have first the first reaction followed by the second reaction. So adding that together, this cancels out, and so what you have is only N2 plus this oxygen that gives you the NO2, which is the product. And so this minus this actually plus this, but because this is a negative sign, so the delta H is 33. Right, so you can also represent this as an energy diagram. Now let's look at another example. So what is the delta H of CS2? What is the standard enthalpy of formation for CS2 given the following thermochemical equation? So really what you need to do is rearrange this equation. Now clearly this is at the product side. So you need to reverse this so that it is not a reactant. Sorry, this is in the reactant side, at the reactant side. So you want this as a product. So it should be reversed. So when that is reversed, that becomes positive. And in some cases like this, you have to actually multiply that by 2. And then you can do the simultaneous equation and you get 86.3. Now, you can't just watch this without you actually practicing this. So what I want you to do is look at this equation without looking at the solutions and try to do it yourself and then double check. Okay, practice makes perfect. All right, so benzene burns in air to produce carbon dioxide and liquid water. How much heat is released per mole of benzene combusted? So the heat of formation of benzene is 49.04. All right. So you want to determine the heat change. All right. So that means you want that plus that gives you CO2 plus water. So the products minus the reactants will give you, can also be expressed in this way. All right. So you can do this in terms of this, or you can do that in terms of the simultaneous equation. All right. So another expression here. So you can do this. You have water plus carbon. That gives you hydrogen and carbon dioxide. The first method is by doing the simultaneous equation. And the second method by taking the HF products minus HF the reactants, and both will give you the same answer. Whichever method that you choose that you're comfortable with, so long as it is correct and done carefully. All right. So as I said, you have different types of reaction involving the enthalpy, and one of them is also solution. Delta H of solution. So an example is given the lattice energy of sodium chloride and the heat of hydration of Na plus and Cl minus, calculate the heat of solution. So then finding the delta H of solution is equals to that of ionization minus that of the hydration gives you 4 joules. So you have 8 solid examples to actually practice, and I think that will make you quite solid in this enthalpy part. All right, so that's all for these slides for this part of the lesson. So this is not your attendance, but this is actually a video that I want to share so that you'll be inspired, and so that you can take a short break before we actually go on to our next lesson. All right, till then, see you again. Assalamualaikum. Bye for now.